Jai Hind to all. Myself Richa, Assistant Professor in the Department of Electronics and Communication of Ajay Kumar Garg Engineering College. Today we will discuss about microwave component and basically the isolator, circulator and directional coupler. So as we know, first we will discuss about the ferrite device. Ferrites are the non-magnetic material with a resistivity nearly 10 to the power 14 and greater than the metal and with dielectric constant of 10 to the 15 and relative permittivity of the order of 1000 when we compare it with the metals, and they have magnetic property similar to the ferrous material. They are oxide, which is a compound having general composition of the form of MEO Fe2O3, that is, it is a mixture of metallic oxide and a ferric oxide, where Mu represent any divalent metallic oxide and ferric oxide, whereas any divalent metallic oxide such as MnO, ZnO, CdO, NiO or a mixture of these. It means we can use any type of MEO type of material here. So how they can be formed? They are obtained by firing powdered oxide of material at 1100 degrees Celsius or more, right? And after that they will be pressing into different shape. By doing this process, the ferrite device are added some characteristics of ceramic insulator so that they can be used at microwave frequency. And the ferrites have strong magnetic property. Because of all these property, ferrite find application in number of microwave devices to reduce reflected power for modulation purpose and in the switching circuits. And because of the high resistivity, they can be used up to 10 gigahertz frequency. So ferrite have one more important property which is useful at microwave frequency, that is non-reciprocal property. So basically in the microwave we will use this property of ferrite devices. What is that? When two circularly polarized wave, one rotating clockwise and another in anti-clockwise, are made to propagate through ferrite material, it will react differently to two rotating fields and thereby presenting different effective permeability to both the waves. It means if same circularly polarized wave which is rotating in clockwise and anti-clockwise direction and it will propagate through the material will behave differently for both the rotating fields. So here we will discuss what is Faraday's rotation. So consider a infinite lossless medium. So see here I am considering one ferrite device. This is your port number 1, port number 2 and length of the device is L. So static B0 is applied along the Z direction. Z is the direction of propagation. So here we are applying a magnetic field B0. A plane TEM wave that is linearly polarized along the axis at t is equal to 0 is made to propagate through the ferrite in Z direction. The plane of polarization of this wave will rotate with distance, and this phenomena is known as the Faraday's rotation, right? So how this wave will be behaving after traveling a particular distance is given by the Faraday's rotation. So see here, this is your device which is placed into x and y direction, and one magnetic field is applied along Z direction. This is your magnetic field and Z is the direction of propagation. So in the direction of propagation, one magnetic field is applying. So any linearized waveform that can be regarded as a vector sum of two counter rotating circularly polarized waves. So the ferrite materials offer a different characteristic to these waves, with the result that phase change for one wave is larger than the other wave. If phase change is different, so there will be a resulting rotation of theta will be there. and this rotation theta of linearly polarized wave at a distance of z is equal to L. It means if in the direction of propagation one linearly polarized waveform is given, so because of the rotating circularized wave, it will be having two phase. It means it will behave differently for both the type of rotation. So one wave is larger than the other and there will be a formation of angle theta. And what is that theta? If the direction of propagation is reversed, then the plane of polarization continue to rotate in the same direction, which is from z is equal to L to z is equal to 0. Here z is equal to L is the length of your device, and the wave will arrive back at z is equal to 0, polarized at an angle of 2 theta. So in fact, this angle of rotation theta is given by L by 2 of beta plus minus beta of minus. Now what is beta plus? Beta plus is the phase constant for right circularly polarized wave, and beta minus is the phase constant for left circularly polarized wave. So ferrite rotation in ferrite. Thus, when a wave is transmitted from port 1 to 2 in the ferrite device, it undergoes a rotation of anti-clockwise direction. And even if the same wave is allowed to propagate into the reverse direction, or we are saying that from port 2 to port 1, it will undergo in the same direction. It means rotation is not going to change when the wave is traveling from 1 to 2 or 2 to 1. Hence, direction of rotation of linearly polarized wave is independent of the direction of the propagation. So first device is the ferrite device is the isolator. See here, this is the diagram of your isolator. We can say this is the picture of the isolator which is used in the microwave devices, microwave circuits. So this is the isolator, and one arrow defines that wave is propagating into, arrow defines direction of propagation. So it means wave will travel from here to here. This arrow will show the direction of the propagation. And isolator is a two-port device. This is your port number 1, and in this side there is a port number 2, right? So when very small, it means it will provide attenuation, very small attenuation when wave is propagating from port 1 to port 2 in this direction, because wave is propagating into this direction. But it provides maximum attenuation for the transmission from port 2 to 1. It means if wave is traveling into the opposite direction, isolator will provide maximum attenuation. So basically this is used to isolate two particular devices. The reflected wave should not be allowed to reach the microwave generator, which will cause amplitude and frequency instability of the generator. That's why the first component after microwave source is the isolator, because it will isolate any reflection from the load to the source to protect the generator, and it is a non-reciprocal device. This is the main property of the ferrite device which we are using in the microwave signals. So see here, this is your microwave source and load, and if we want to save our source, we will attach one isolator in between source and load. So wave will be allowed to pass through from port 1 to 2, but it will not allow to pass through 2 to 1, right? So an ideal isolator completely absorbs the power for propagation in one direction, and it will provide lossless transmission in the opposite direction. So now we will first discuss about the construction of isolator. See here, this is the internal diagram of the isolator, how it will behave. So this is your input waveguide. After that, one resistive van, or we can say resistive card, is placed after this waveguide. After that, one ferrite rod is used here. After that, again one resistive card is placed here, and this is your output waveguide. Then how and at which angle these are used? So isolator can be made by inserting ferrite rod. This is your ferrite rod along the axis of the rectangular waveguide. It means it is placed along the axis of the waveguide. The input resistive card, this is your input resistive card, is in the YZ direction and output resistive card is at 45 degree with respect to input card. It means if it is at this angle, 0 angle, so it will be at 45 degree angle, right? And the DC magnetic field is applied longitudinally to this ferrite rod, which will rotate the plane of polarization by 45 degree. Now an input, if I am giving input at TE10, okay, input TE10 mode wave is incident in input port. Since it is perpendicular to the resistive card, there will be no absorption of the power because it is in parallel, right? Since it is a perpendicular to the resistive card, so any microwave signal, if it is perpendicular to the resistive card, will not absorb by the card, and if it is parallel to the resistive card, then wave will be completely absorbed. So this card is placed perpendicular to the resistive card, so there will be no absorption of the power. And it is after that, when wave is not absorbed by it, it will be passed through your ferrite rod, and it is rotated by ferrite rod with 45 degree. Why this 45 degree? Because we are applying a DC magnetic field longitudinally along the direction of your ferrite rod, and it will create a angle of 45, polarization angle of 45 degree. So does the wave appear at the output without any attenuation? Why? See here. So 45 degree rotation is given here, and again 45 degree rotation is coming out. Again 45 degree rotation is there. So your wave will be completely out from port number 2 without any attenuation. So on the contrary, reflected wave from the output and is further rotated by ferrite rod with an angle of 45 degree in the same direction. Thus the resultant polarization wave is parallel to the input resistive card. This wave is completely absorbed by the card. It means if we are moving into the reverse direction, it means now here wave is we are giving input at port number 1. So what will happen at port number? Input is given at port number 2. So what will happen at port number 1? So you can say that wave is entering with the angle of 45 degree. Again 45 degree rotation is given by this resistive card, and now your wave will become parallel to this resistive card. And if the wave is parallel to the resistive card, it will be completely absorbed by the card, and you will not receive anything at the port number 1. It means no wave at port 1. So see, this is the complete construction of the isolator. This is your port number 1. This is input resistive card, and here 45 degree twist is given by the isolator geometry. After that, one ferrite rod is placed, and here we are applying one static field of D0, and this is your port number 2. See here, your TE10 mode is coming here. Now because of this twist, this resistive card will allow signal to propagate. Now this 45 degree rotation is given by this twist. It means now your wave is rotated by 45 degree, right? And its ferrite rod is also given a 45 degree rotation, so it will given rotation into this direction. So this 45 degree in this direction and this 45 degree in this direction, so this will be nullified and your wave will be in your original form of TE10, and this will pass through port number 2. In some type of isolator, this type of construction is also provided here, where 45 degree twist is given by the geometry itself, right, at input port. So in the reverse direction, what will happen? Now we are giving input at port number 2. Okay, so signal is entering into this isolator at port number 2. So it will, this resistive card will allow signal to propagate. After that, this ferrite rod will give the rotation into this direction, right? After that, there is a twist of 45 degree. So it will again give 45-degree rotation in the same direction. If in the same direction, so these two angles will be added up, and here the waveform will become your parallel to your resistive card, and this resistive card will completely absorb the waveform. So you will not get anything at port number 1 in the reverse direction. So now we will discuss about the scattering matrix of an ideal isolator. As we know, your isolator is two-port device. Isolator is two-port device. So it means it is having two port, and total element in the S matrix is 2 by 2, that is 4. So S matrix elements are S11, 12, 13 and 22. Now we will discuss various property of the isolator. If both ports are perfectly matched to the junction, it means there is no reflection from the port itself. It means if ports are perfectly matched, then S11 and S22 both will be 0. Anything which you are giving at port number 1 will not reflect back to port number 1, and anything which is given to port number 2 will not reflect back to port 2 itself, because both are perfectly matched. Next condition, an ideal oscillator completely absorbs the power for propagation from port 2 to 1. It means any signal which is given at port number 2 will not received at port number 1. So it means scattering parameter of S12 will be 0. Third, it provides lossless transmission from port number 1 to 2. It means any power which is given at port number 1 will be 100% received at port number 2. So it means anything which is given at port number 1 will be received by 2, that is 100%, so it is equal to 1. So if I am using all the three property, then your S matrix will become, so what is the conclusion here? S11 is 0, S12 is, see here, S12 is also 0, S13 is your 0, or your S22 is, this is your S21, right? So S21 is 1 here, right? And S22 is 0. So I can rewrite the matrix. S11 is 0, S12 is 0, and 21 is 1, and S22 is 0. So in this way, we can find out the S matrix of ideal isolator. So second ferrite device is the circulator, right? So now we will discuss about the circulator. So as its name specifies, circulator, it means any shape of the devices in the circular. So circular, here if I am discussing, this is your 3-port circular. Circulator, right? And this is your 4-port circulator. So microwave circulator is multi-port waveguide junction, in which wave can flow from nth port to n plus 1th port in one direction. It means if it is a 3-port circulator, then signal will be propagating into 3 ports. If it is 4-port, then 4-port. But condition is that it will allow the signal to propagate into only next port itself. It means if anything which is coming into the port number 1, it will be going to port number 2, not in port number 3, right? And 2 is connected to 3, and 3 is connected to 1. In the reverse direction, this propagation is not possible. If it is a 4-port device, see here, if any signal which is entering into port number 1, it is connected with port number 2, 2 is connected with 3, 3 is connected with 4, and 4 is connected with 1. So although there is no restriction in number of port, but basically we are using 3-port and 4-port microwave circulator commonly in the microwave devices. Again, this is your non-reciprocal device. So this property we will use it here. It has peculiar property that each terminal is connected only to the next clockwise terminal. So this is the construction of the circulator. See here, this is your port number 1, port number 2, 3 and port number 4, right? Okay. So see, any wave which is coming into the port number 1, this is your rectangular, this is a conversion of rectangular to circular. So your waveform TE10 is entering here and here it will become TE11 because of the your rectangular wave is converted into the circular, right? And this port is placed perpendicular and here one ferrite rod is taken which is at the angle of 45 degree and port number 4 is at 45 degree and port number 2 is again at the 45 degree, or we can say this line is parallel to port number 1. This, if we are comparing the position of port number 1 and 2, so port number 2 is at the 45 degree as compared to port number 1. So first we will discuss how it will be working. So as we 1 is connected to 2, 2 is connected to 3, 3 is connected to 4 and 4 is connected to 1. See how the waveform which is entering into this waveguide is converted into TE1. Now this waveform are coming like this. This port is perpendicular to this waveform. It means port number 3 will not absorb power which is coming from port number 1. It will leave that power. So this power is moving into this direction and here a rotation of 45 degree will come, right? So this rotation of 45 degree will come. Now this 45 degree and this 45 degree, it means this incoming wave is now perpendicular to port number 4. So again the port number 4 will not absorb this power and this wave will now move here. Okay. So wave which is coming at 45 degree and this port 2 is placed at in the opposite direction at the angle of 45 degree. So these two angles will be cancelled out. Now incoming wave is in parallel with the port number 2 and this wave will be out from port number 2. Okay. So the wave which is entering from port number 1 leave port number 3 and port number 4 unaffected. It will be out from port number 2, right? So I can take another example that if wave is entering from port number 2, right? So if wave is entering from port number 2, this is at the angle of 45 degree and it come to the port number 4. So this 45 degree plus 45 degree, it means this is 90 degree. So wave entering from port number 2 is perpendicular to port number 4. So port number 4 will not absorb this waveform. Now it will be going to this ferrite rod. So ferrite rod is in the direction of opposite direction. So now this wave is coming to this port number 3 and this will be now parallel to port number 3. So this wave is absorbed by this port and output will be taken at port number 3. So scattering matrix of an ideal isolator. So this is the scattering matrix of 3-port ideal circulator, right? So it is 3-port, it means the order of the matrix is 3 into 3. 9 elements are there. So 9 elements, so this, all these elements are 1, right? Or if I am saying 1 is connected to 3, 3 is connected to 2, 2 is connected to 1. Okay. In this way, 4-port ideal circulator, it means input output ports are 4. So total elements are 16, 4 by 4 matrix. Okay. So port 1 is connected to 4, 1 is connected to 4 and 4 is connected to 3, 3 is connected to 2 and 2 is connected to 1 in this way. So from these combination we can find out the value of S parameter matrix. What is the value of different element of S matrix? So now we will discuss about the application of the circulator. So first application of the circulator is in the radar antenna. See here we are using 3-port circular here. At port number 1 transmitter is connected, port number 2 receiver is connected, and port number 3 receiver is connected, at port number 2 antenna is connected, right? So the signal which is transmitted will completely isolated from the receiver, and anything which is received at the receiver is completely isolated from the transmitter. So basically this type of circulator is used to save transmitter and receiver, or we can say the isolate transmitter and receiver. If there is some reflection from the receiver, it will not harm your transmitter. Next application of the circulator, it can be used into the tunnel diode amplifier. See here, this is again 4-port circulator. At port number 1 input is given, port number 2 tunnel diode is connected, and port number 4 is used as a match termination, and output is taken as port number 3. So the means of separating the input and output in a ferrite circulator, here basically input and output we are separating using this circulator. Signal incident at port number 1 are directed to port number 2. Any reflection from port number 2 are directed to port number 3 here. It means if you are giving anything which is at the port number 1, it is going to port number 2, and if any reflection is coming, so as the property of the circulator says, it is connected to next port in the in this direction only. So any reflection will go to the port number 3 itself, right? And you can use 4 or 5-port circulator are used to gain additional isolation between input and output ports. So how it will operate? Operation of circulator type of tunnel diode amplifier is as follows. The input signal at port number 1 is directed to the tunnel diode modulate at port number 2, which is connected at port number 2. The amplified signal reflected from tunnel diode enters at port number 2 and is directed to port number 3. It means if there is reflection from the tunnel diode, it will be sent to the port number 3, which is the output port. If port 3 is not perfectly matched, right? If port 3 is not perfectly matched, reflection from the terminals are absorbed in the load at port number 4, because port number 4 here we have connected it with the matched load. So this complete reflection will be absorbed at port number 4. So next microwave device is the directional coupler. So basically directional coupler is used to give the direction of microwave power. So this is the practical diagram of the directional coupler. Basically 4 ports are there, port number 1, 2, 3 and 4. One port is terminated. Basically this is completely matched port, so it is terminated port number 4. So this is the internal diagram of the waveguide. Here basically 2 waveguides are connected. Port number 1 and 2 are the primary waveguide. So any signal which is coming, it will be directed here, and some part is coming here and some is coming here. So this is your main waveguide, and port number 3 and 4 are the auxiliary waveguide, or we can say these are the secondary waveguides, right? So it is a 4-port waveguide junction. It consists of a primary waveguide of 1 and 2 port and secondary waveguide 3 and 4 port. So directional coupler can be realized in microstrip, strip line, coax or waveguide. It means for transmission of microwave signal, directional coupler is used to connect 2 microwave signals or give direction to these 2 microwave signals. So directional coupler has 4 ports, whereas one is regarded as input. This is your input port, as the port where most of the incident signal exists. One is regarded as the coupled port, right, where a fixed fraction of the input signal appear and usually expressed in dB. And one is regarded as the isolated port, which is usually terminated, right. So if I am taking about port number 1, so this is your port number 1, which I can say that it is your input port, and This port number 3 is the isolated port for this, and port number 4 is used as where the fraction of the power is coupled. This is your coupled port, right? And 2 is your output port. So ideal directional coupler can be summarized as a portion of power traveling from port number 1 to 2 is coupled to port number 4, and 3 is used as an isolated port, right? So wave is going into port number 1 to 2, some part is going into port number 4, and this is your isolated port. A portion of power traveling from port number 2 to 1, if in the reverse direction, 2 to 1, right? And it is coupled to port number 3, and it is isolated at port number 4. A portion of power incident on port number 3 is coupled to port 2, but not to 1. It is coupled to port number 2, not to 1, but not to. So similarly, a portion of power incident at port number 4 is coupled to port number 1, not to port 2. So port number 1 and 3 are isolated, and port 2 and 4 are isolated. Okay. So 1 and 3 are isolated port, and 2 and 4 are isolated ports. So practically, small portion of input power at port number 1 is also reflected at port number 4. See here. So Pi is the incident power, PR is the reflected power at port number 2, PF is the forwarded coupled power, PB is the reflected power. So if I am taking this, this is your Pi, this is your PR, received power and forward power, and this is your backward power. So coupling factor and directivity are the two important parameters of your direction coupler. Coupling factor is the measure of how much of the incident power is being sampled, while directivity is a measure of how well the directional coupler distinguishes between forward and reverse traveling waves. So parameter of directional coupler, coupling factor can be calculated by 10 log Pi by Pf, directivity 10 log forward power upon backward power, isolation can be calculated as 10 log Pi by Pb, insertion loss can be calculated as 10 log Pi by PR, and total isolation can be written as directivity plus coupling in dB. So the ideal coupler has infinite directivity and isolation. Directivity is defined in terms of coupling factor. For 3 dB directional coupler, it means C is equal to 3 dB. So here we will discuss about the derivation of S matrix. Since it is a 4-port device, it means it is a 4x4 matrix. All the ports are perfectly matched at the junction. It means S11, 22, 33, 44 all are 0, because all are perfectly matched, so there is no reflection. From the symmetric property, it means what is symmetry? S of ij is equal to S of ji, right? Ji. 2, 3 is equal to 3, 2, 1, 3 is equal to 3, 1, 2, 4 is equal to 4, 2, 3, 4 is equal to 4, 3, 4, 1 is equal to 1, 4. And it is the ideal direction coupler. It means port 1 and 3 are isolated. It means P31 is equal to 1, 3. And again, port 2 and 4 are isolated. It means port 2, 4 is equal to 4, 2. So this S matrix can be rewrite as S11 is 0, S12, S13 is 0, S41 0, 1, 2, 0, 2, 3, 0, 0, 2, 3, 0, 3, 4, 1, 4, 0, 3, 4 and 0. So here we are assuming a lossless network, and we are using unitary property and zero property. What is the unitary property? That is S of complex conjugate of S is equal to I. So after that we are using matrix property, and we are getting the 4 equation. S12 square plus S1 square is equal to 1, S12 square plus S23 square is equal to 1, S23 square plus S34 square is equal to 1, 1/4 square plus S of 3/4 square is equal to 1. S of 1, 2, S of 2, 3 complex conjugate plus S of 1, 4, S of 3, 4 complex conjugate is equal to 0. So from equation 1 and 2, from these two equation, as it means these both are same and this side is also same. So I can write S14 is equal to S of 2, 3. Now from equation 2 and 3, from these two equation. So these two are same and 1 is same. So S12 is equal to S of 3, 4. And let us assume the power at S12 is equal to S34 is equal to P, where P is any positive and real number. So I can write P of S here in place of S12, I will write P. P of S23 complex conjugate plus S23 is equal to 0. It is from equation 4 and 5 and 6. As we know, P is not equal to 0. So this factor will be 0. It means S23 will be complex conjugate J of Q. So I am taking minus JQ here. By using it means it is must be a imaginary quantity. So S23 and 14 is equal to JQ, where Q is a positive and real number. Equation 5 can be written as P square plus Q square is equal to 1. So substituting all the values, this is the final matrix of isolator: 0 P 0 JQ, P 0 JQ 0, 0 JQ 0 P, JQ 0 P and 0. Thank you very much. In the next lecture, we will discuss some another topics of microwave.